In December of 2024, inside a laboratory chilled to temperatures colder than the darkest corners of outer space, something happened that the world wasn't ready for. Google's lead quantum scientist, Hartmut Neven, was reviewing the first round of benchmark results from the team's newest quantum processor, a chip they called Willow. The numbers on his screen didn't make sense, not because they were wrong, but because they were so right, so far beyond what anyone had calculated was possible that the only rational response was to run the tests again, and again, and again. The results didn't change. In under 5 minutes, that chip had completed a computation that would take the most powerful classical supercomputer on Earth 10 septillion years to finish. For context, 10 septillion years is not just longer than a human lifetime, or longer than recorded history, or even longer than the age of the Earth. It is a number so large, it dwarfs the entire age of the universe, and by a factor that makes the universe itself look like a blink. And Google had done it in the time it takes to make a cup of coffee. But here's the thing. The Willow chip was only half the story. What nobody was talking about, what the mainstream headlines almost completely missed, was what an AI system called Grok 3 had quietly uncovered months earlier. And when you put these two things together, when you take what Grok found buried inside Google's own public data and line it up against what Willow then demonstrated in the lab, you begin to see something that goes far beyond a single technological achievement. You begin to see the outline of a future that is arriving much, much faster than any expert predicted. A future where the rules of computing, encryption, medicine, and global security are all being rewritten simultaneously. To understand why any of this matters, you first need to understand what quantum computing actually is, because the name alone tends to inspire either confusion or skepticism, and neither reaction is useful here. Classical computers, the ones running every app, every website, every email, every spreadsheet in the world right now, operate on bits. A bit is a switch. It is either off or on, 0 or 1. Every piece of software ever written is ultimately just an enormous sequence of these tiny switches, flipping at incredible speed. That's the foundation of all modern computing. It's powerful, it's fast, but it has a ceiling. There are certain categories of problems so complex, with so many possible combinations, that even the fastest supercomputer in existence would need longer than the life of the universe to explore all the options. Quantum computers are fundamentally different in a way that sounds like science fiction until you see the evidence. Instead of bits, they use qubits, and a qubit doesn't have to be 0 or 1. Thanks to a property called superposition, a qubit can be both at the same time. It can exist in every possible state simultaneously until the moment you measure it. Add to that a second quantum property called entanglement, where two qubits become linked so that the state of one instantly influences the other, regardless of distance, and you suddenly have a machine that doesn't solve problems by checking answers one at a time. It explores entire solution spaces in parallel. It doesn't walk through the maze. It exists in all paths of the maze at once and finds the exit instantaneously. The problem, for the 30 years since quantum computing became a serious field of research, has been noise and error. Quantum states are extraordinarily fragile. The slightest vibration, the tiniest fluctuation in temperature, the faintest electromagnetic interference, any of these can cause a qubit to lose its quantum state, a phenomenon called decoherence. Early quantum computers were fascinating proofs of concept, but they were wildly unreliable. Adding more qubits didn't solve the problem. It made it worse. More qubits meant more interactions, more chances for error, more noise cascading through the system. The dream of a truly useful quantum computer felt perpetually out of reach. Always 10 years away, always just beyond the next breakthrough. What Google's Willow chip demonstrated was something that had existed only in theoretical physics papers for nearly 3 decades, a principle called below-threshold error correction. The idea is almost counterintuitive. What if, instead of errors multiplying as you add more qubits, they actually decreased? What if the system became more stable, not less, as it scaled up? That's what every quantum physicist knew needed to happen. That's what every quantum physicist also assumed was essentially impossible with current hardware. Willow made it reality. The chip is self-stabilizing. It gets more accurate as it gets more powerful. And that single property, that one breakthrough in error correction, is the key that unlocks everything else. Because it means that for the first time in the history of quantum computing, you can build a larger machine and trust that it will perform better, not worse. Now here is where Grok 3 enters the story, and this is the part that gets genuinely strange. Grok 3 is an AI system developed by xAI, Elon Musk's artificial intelligence company. In early 2024, researchers gave Grok 3 a task that sounds straightforward but was, in practice, an enormous undertaking. The task was this: take everything that Google had ever made publicly available, every patent filing, every research paper, every technical document, every infrastructure report, every hiring pattern, every academic conference abstract with Google's name attached, and read it all together, simultaneously, looking not for any single piece of information, but for the patterns that emerge when all of it is considered at once. This is something a human researcher cannot do, not because humans aren't intelligent enough, but because there is simply too much data spread across too many sources, covering too many years, for any individual mind to hold at once. Grok 3's architecture, on the other hand, is built precisely for this kind of analysis. It doesn't read documents one at a time and summarize them. It maps the relationships between them. It notices when a particular word appears more frequently in one year's patent filings than another. It detects when a research team's publications suddenly go quiet in a specific area, which often signals that the work has moved from public research into classified or proprietary development. It tracks when certain engineering roles start appearing in job listings that didn't exist before, and from all of these signals, taken together, it builds a picture. What Grok 3 found was not one discovery, it was three, and they converged on the same conclusion from three different directions. The first discovery was in the patent data. Over several years, Google's quantum-related patent filings had been quietly shifting in a very specific direction. The early patents were almost entirely focused on superconducting qubits, the type of qubit that Sycamore, Google's previous flagship quantum processor, used. But in more recent filings, a different word started appearing with increasing frequency: topological qubits, topological quantum computing. This is a radically different approach to building a quantum computer, one that most of the industry had dismissed as theoretically elegant but practically impossible. Topological qubits are built around exotic quantum states that exist at the boundaries of certain materials, involving particles called Majorana fermions that are their own antiparticles. They are far more stable than superconducting qubits. They are naturally more resistant to the decoherence problem, and Google, according to its own patent history, had been quietly building toward them for years without making a single public announcement. The second discovery came from the raw experimental data of the Sycamore processor. During a routine calibration process, Grok 3 flagged something that the research team had noticed but not fully understood. Clusters of qubits inside Sycamore were producing repeating outcomes in ways that defied the expected probabilistic behavior of quantum systems. Quantum computing is built on the assumption that qubit behavior is inherently random until measured. But what Grok found were patterns. Faint, recurring statistical regularities appearing where there should have been noise. When the data was visualized, what emerged looked like waves, a hidden rhythm beneath the randomness, a structure that shouldn't exist. Scientists offered several competing theories to explain it. Some proposed that it represented a form of quantum memory, residual information from previous computations somehow bleeding into subsequent operations, like an echo that the chip couldn't fully silence. Others went further, suggesting that the patterns might indicate the chip was interacting with quantum fields in ways that current physics doesn't fully account for. A small number of researchers, writing in papers that attracted both serious attention and serious skepticism, raised the possibility of something far more exotic, that the chip might be accessing quantum states that exist across different computational branches, different timelines, in the language of certain interpretations of quantum mechanics. Most physicists firmly rejected that last interpretation, but even the skeptics agreed that the patterns themselves were real. Whatever was causing them was not fully understood. The third discovery Grok made was perhaps the most practically alarming of the three, and it didn't involve physics at all. It involved cryptography. As Grok 3 analyzed the trajectory of Google's quantum research alongside recent improvements in quantum algorithms, it began generating projections about the timeline for what security researchers call a cryptographically relevant quantum computer, a quantum machine powerful enough to break the encryption that protects essentially all digital communication on Earth. RSA encryption, elliptic curve cryptography, the mathematical locks that protect bank transfers, private messages, classified government intelligence, medical records, trade secrets, all of it, every encrypted communication you've ever sent, every password you've ever created, every financial transaction ever recorded, all of it protected by a form of mathematics that, in a post-quantum world, will be as easy to crack as a combination lock with the combination written on the outside. Grok's projections, cross-referenced against Google's own published research on algorithmic efficiency improvements, suggested that the window of safety was much narrower than the public understood. And what happened next confirmed it. On February 7th, 2026, Google made an announcement that sent shockwaves through every government security agency, every major financial institution, and every technology company that had been paying attention. The company issued an urgent public warning. Current encryption systems, Google said, are already under attack. Not in the future. Now. Adversaries and the word used was adversaries, not hypothetical future adversaries, are already harvesting encrypted data. They are collecting it in massive quantities and storing it with a very specific plan to decrypt it later once a sufficiently powerful quantum computer becomes available. This strategy has a name. It is called Store Now, Decrypt Later, and it means that your encrypted communications from today are not secure in any meaningful long-term sense. They are being archived, waiting for the key that will eventually exist. Google also revealed something that underscored the urgency more clearly than any warning could. The company had already completed the migration of its own internal systems to quantum-resistant encryption, a new class of cryptographic standards called post-quantum cryptography, finalized by the National Institute of Standards and Technology just the year before. Google had not waited. It had seen what was coming and had moved. The question was whether anyone else would move fast enough. Then came the March announcement, and the timeline suddenly collapsed. Google's VP of Security Engineering published a paper in March of 2026 that revised the company's estimates for how many physical qubits would be needed to break RSA 2048 encryption, the standard protecting most of the world's internet traffic. The previous estimates had placed that number in the millions, a figure that provided some comfort because current quantum hardware was nowhere near that scale. The new estimates were dramatically lower, and Google announced a 2029 deadline, not for when a cryptographically relevant quantum computer might exist somewhere in theory, but for when Google itself would have completed its own migration away from vulnerable encryption. That 2029 deadline, coming from the same researchers producing the quantum hardware, was the clearest possible signal that they believed the threat was not decades away. It was years away. The implications of this are hard to fully absorb because they affect everything simultaneously. For individuals, it means that data you assume is private may already be in someone else's hands, waiting to be read. For governments, it means that classified communications from the past decade may eventually become readable by foreign intelligence services with access to sufficiently advanced quantum hardware. For the financial system, it means that the cryptographic infrastructure underpinning trillions of dollars in daily transactions is operating on borrowed time. For cryptocurrency specifically, it means that the mathematical principles securing Bitcoin and Ethereum wallets, elliptic curve cryptography, are among the most vulnerable because blockchain ledgers are public by design, meaning the encrypted data is already stored and accessible to anyone who wants to harvest it for later decryption. What makes the Google Grok story so important is not just the individual discoveries, it is what they reveal about the nature of scientific progress in the age of advanced AI. For most of human history, scientific breakthroughs have been the product of individual genius and collective effort, moving forward one experiment at a time, one publication at a time, one peer review at a time. The pace of discovery has always been limited by the pace at which human minds can absorb, synthesize, and act on information. What Grok 3 demonstrated, and what more powerful successors are demonstrating even more dramatically, is that this limitation no longer applies in the same way. An AI system given access to the complete body of publicly available research in a field can identify connections and patterns that no human researcher, working with any team over any timeline, could reliably find. It can see the entire forest and every tree simultaneously. It can detect when the absence of certain publications is itself meaningful. It can map the intersection of fields that humans tend to keep siloed: quantum physics and cryptography, materials science and computing architecture, hiring trends and research direction, and from those intersections, generate predictions that turn out to be accurate months or years before the underlying technology is publicly announced. This creates something new in the history of science, an accelerant. AI doesn't replace human researchers. It doesn't do the experiments. It doesn't sit in the cryogenic lab at 3 a.m. debugging a qubit calibration protocol. What it does is compress the time between discovery and understanding. It takes the insights that might have taken a decade of cross-disciplinary collaboration to emerge naturally and surfaces them in weeks. And in a field moving as fast as quantum computing, that compression is not a minor efficiency gain. It is a transformation of the entire pace of progress. What comes next is already being shaped by everything described here. The quantum computing landscape of 2026 looks nothing like the landscape of 5 years ago. Where there was once theoretical promise and incremental experimental progress, there is now verifiable, reproducible quantum advantage, demonstrated on hardware, published in Nature, confirmed by independent researchers. Where there was once comfortable consensus that cryptographically relevant quantum computers were decades away, there is now a 2029 deadline set by the company best positioned to know. Where there was once the uncertainty about whether AI systems could meaningfully accelerate scientific discovery, there is now concrete evidence that they can, and that the patterns they find in public data can predict proprietary breakthroughs before those breakthroughs are announced. The industries most immediately affected are not abstract. Healthcare stands to benefit enormously from quantum computing's ability to simulate molecular behavior at the quantum level, modeling protein folding, predicting drug interactions, designing therapies targeted to individual genetic profiles in ways that classical computers simply cannot replicate. Materials. Science is another frontier where quantum simulation could compress decades of laboratory trial and error into months of computational modeling, potentially yielding breakthroughs in battery technology, semiconductor design, and materials with properties we haven't yet imagined. Climate modeling, one of the most computationally demanding problems in science, could be transformed by quantum systems capable of handling the full complexity of Earth's atmospheric and oceanic systems simultaneously. But none of these benefits exist in a vacuum. Every one of them is accompanied by the same quantum threat to encryption, the same narrowing window, the same urgent need for a global infrastructure transition that most organizations haven't yet begun. And here's the sobering reality that gets lost in the excitement about quantum's potential. The technology that makes all these wonderful applications possible is the same technology that makes the digital locks protecting all human communication vulnerable to being broken. There is no version of quantum progress that includes only the benefits without the risks. They are inseparable. What is perhaps most striking about everything that has unfolded, from Grok's analysis to Google's Willow chip to the March 2026 encryption warning, is not any single discovery in isolation. It is the speed at which reality has caught up with what were, just a few years ago, considered wildly speculative timelines. In 2019, when Google first claimed quantum supremacy with its Sycamore processor, the scientific community was deeply skeptical.